So can I get a show of hands, how many of you in this room have been in a plane in this past year? Yeah, that's pretty good. Well, it turns out that you share that experience with more than 3 billion people every year. And when we put so many people in all these metal tubes that fly all over the world, sometimes things like this can happen, and you get a disease epidemic. I first actually got into this topic when I heard about the Ebola outbreak last year. And it turns out that although Ebola spreads through these more range-limited large droplet routes, there's all these other sorts of diseases that could be spread in the airplane cabin. The worst part is, when we take a look at some of the numbers, it's pretty scary. So with H1N1, there was this guy that decided to go on the plane and in a matter of a single flight actually spread disease to 17 other people. And then there's this other guy with SARS who managed to go on a 3-hour flight and spread the disease to 22 other people. That's not exactly my idea of a great superpower. When we take a look at this, what we also find is that it's very difficult to pre-screen for these diseases. So when someone actually goes on a plane, they could be sick, and they could actually be in this latency period in which they could actually have the disease but not exhibit any symptoms. And they could, in turn, spread the disease to so many other people in the cabin. And how that actually works is that right now we've got air coming in from the top of the cabin and from the side of the cabin, as you can see in the blue. And then also that air goes out through these very efficient filters, eliminates 99.97% of pathogens near the outlets. And what happens right now, though, is that we have this mixing airflow pattern. So if someone were to actually sneeze, that air would get swirled around multiple times before it even has a chance to go out through the filter. So I thought, okay, this was clearly a pretty serious problem. And I didn't have the money to go out and buy a plane, so I decided to build a computer instead. It actually turns out that with computational fluid dynamics, what we're able to do is create these simulations that give us higher resolutions than actually physically going in and taking in readings in the plane. And so how essentially this works is you would start out with these 2D drawings. These are floating around in technical papers around the internet. I take that and then I put it into these 3D modeling software, really building that 3D model. And then I divide that model that I just built into these tiny pieces, essentially meshing it so that the computer could better understand it. And then I tell the computer where the air goes in and out of the cabin, throw in a bunch of physics, and basically sit there and wait until the computer calculates the simulation. So what we get, actually, is with the conventional cabin is this. You'll notice the middle person sneezing. And we go splat, it goes right into people's faces. It's pretty disgusting. And from the front, you'll notice those 2 passengers sitting next to the central passenger, not exactly having a great time. And when we take a look at that from the side, you'll also notice those pathogens spreading across the length of the cabin. First thing that I thought was, this is no good. So I actually conducted more than 32 different simulations, and ultimately, I came up with this solution right here. This is what I call a patent-pending global inlet director. And with this, we're actually able to reduce pathogen transmission by about 55 times and increase fresh air inhalation by about 190%. So how this actually works is we would install this piece of composite material into these existing spots that are already in the plane. So it's very cost-effective to install, and we can do this directly overnight. All you have to do, put a couple of screws in there, and you're good to go. And the results that we get are actually absolutely amazing. Instead of having those problematic swirling airflow patterns, what we have is we can create these walls of air that come down in between the passengers to create these personalized breathing zones. So you'll notice the middle passenger over here is sneezing again, but this time we're able to effectively push that down to the filters for elimination. And same thing from the side, you'll notice we're able to directly push those pathogens down. So if we take a look again now at the same scenario, but with this innovation installed, you'll notice middle passenger sneezes. And this time, we're pushing that straight down into the outlet before it gets a chance to infect any other people. So you notice the 2 passengers sitting next to the middle guy are breathing virtually no pathogens at all. And we take a look at that from the side as well. You can see a very efficient system. And in short, with this system, we win. So when we take a look at what this means, what we also see is that this not only works if the middle passenger sneezes, but also if the window seat passenger sneezes or if the aisle seat passenger sneezes. And so with this solution, what does that mean for the world? Well, When we take a look at this from the computer simulation into real life, we can see with this 3D model that I've built over here, essentially using 3D printing, we can see those same airflow patterns coming down right to the passengers. In the past, the SARS epidemic has actually cost the world about $40 billion. And in the future, a big disease outbreak could actually cost the world in excess of $3 trillion. So before, it used to be that you had to take an airplane out of service for 1 to 2 months, spend tens of thousands of man-hours, several $1 million to try and change something. But now, we're able to install something essentially overnight and see results right away. So it's really now a matter of taking this through to certification, flight testing, and going through all these regulatory approvals processes. But it just really goes to show that sometimes the best solutions are the simplest solutions. And, 2 years ago, even, this project would not have happened, just because the technology then wouldn't have supported it. But now with advanced computing and how developed our internet is, it's really the golden era for innovation. And so the question I ask all of you today is, why wait? Together, we can build the future today. Thanks.